Hello, everyone. Good day. Welcome to the fourth GeoScience and GeoEnergy webinar. We hope all of you are doing well wherever you are. These webinars are hosted by my friend and colleague Sebastian Geiger from Heriot-Watt and myself from TU Delft. We are especially grateful to our keynote speakers who have joined and supported this initiative for good cause. And of course, thanks to all of you attendees who connect, join, and combat this work from home isolation. We are all proud of being members of this global geoscience community. And in the case you wanted also to watch the videos after the lectures, please visit our YouTube channel, where all videos are released for public use. And also please help us spread the words and make this webinar a good joining time for all of us to connect and see each other for an hour per week. Now to the lecture. It's our pleasure and honor to introduce Professor Matthew Jackson from Imperial College London to you all. Matt is at the Department of Earth Science and Engineering in the chair of Geological Fluid Mechanics. He has received his bachelor's in physics from Imperial College and then PhD from the Department of Earth Sciences at the University of Liverpool in 1997. Since then, he has been affiliated with Imperial College London, first as research associate, then lecturer, and then senior lecturer, and finally professor of geological fluid mechanics. Matt leads research and educational activities on investigation, prediction, quantification, and measurement of transport processes in heterogeneous geological porous media using field, experimental, mathematical, and numerical techniques. He is head of the NORMS group, NORMS is standing for Novel Methods for Reservoir Monitoring, Modeling, and Simulation. And you see the logo of NORMS in his slides already in the top right part. For 5 years, his chair was sponsored by Total between 2011 and 2016. In 2015, he received EAGE Norman Falcon Award. In 2012, he was invited committee member and session chair and presenter of a joint AAPG, SPE, and SEG Helberg conference on fundamentals control on fluid and on flow in carbonates, which took place in France. So kind of a unique combination of many societies. Matt received the 2011 SPE Regional Outstanding Achievement Award, and between 2010 and 11 was the AAPG Distinguished Lecturer. He has been keynote and invited speaker of many events and served in many scientific committees. His publications are listed mostly in his Google Scholar page, published in prestigious journals such as Nature, recently on chemical differentiation, cold storage, and remobilization of magma in the Earth crust. It's our pleasure and honor to host him as our fourth keynote speaker. Please note Matt's lecture would last for about 30 minutes, followed by questions and discussions. Like before, please type in your questions in the chat room to the public, to all, and Sebastian would go through them all and will chair the discussion session. So Matt, the stage is yours. And again, thanks a lot for this kind accepting of our invitation.
Thanks so much, Hadi, and thank you very much, everyone, for connecting in today. What I want to talk about is a method for improved oil recovery, which has attracted a huge amount of attention over the past 10 years from a very wide range of disciplines in science and engineering. And hopefully by the end of this, you'll understand partly why I call it controlled salinity water flooding. You may have heard it described previously as low salinity water flooding, or and terms around that, and also why I continue to think, despite all the attention that's been paid to it, it continues to be a micro to macro scale mystery. As ever, I'd like to thank co-workers for what I'm going to present today, particularly PhD students Harry Kalini, Dawood Al-Marouki, and Abdul Karim Al-Rudan, and postdocs and now lecturer Shuai Li and Jan Vinogradov. So, background. Many of you might be aware that a very common approach to oil recovery is to inject water into the reservoir, and that's done partly to maintain the pressure in the reservoir and partly to displace the oil towards the production wells. And for a long time, there was very little attention paid to the source or the composition of the injected water. So long as it wasn't going to deposit salts or scale in the production tubing, it didn't really matter where it came from. But then there was some very interesting experimental data that came from laboratory core flooding experiments that made people think again. Now, given that I'm going to show quite a lot of results from core flooding experiments, it's perhaps just being clear on what I'm talking about here. So a core is essentially a cylindrical sample of rock, a few centimeters long and a few centimeters in diameter. And in the lab, we can put this in some kind of confining core holder so that we don't allow any flow around or through the sides of the sample. And we can inject fluids into one end of the core and we can produce them from the other. And while we do that, we can measure things like the pressure drop and the flow rate and the electrical conductivity and so forth. And these sorts of experiments are very widely used to try and replicate flow processes in reservoirs, which are buried deep underground, and so we don't have direct access to them. But to do them well, particularly for multi-phase flow, you need to make sure you're replicating the reservoir conditions, which is difficult and expensive. So they're quite expensive and time-consuming experiments to do. And also, if you don't do them very carefully, there are all kinds of experimental artifacts that can invalidate the results. And that's something to bear in mind as we go through and look at some of the results in the rest of the talk. So anyway, people were doing these sorts of experiments, and what they found were results that look something like this. So again, I'm going to show several plots with these axes, so it's probably worth getting our head around what we're looking at. So on the y-axis, we have oil recovery as a percentage of the original oil present in the core sample. And on the x-axis, we have time, which is expressed as a volume of water injected into the core. So we're injecting water here, and we're displacing oil, and we're measuring the volume of oil produced. And what you can see, there's two different oils here, which are the two different lines. So we start off by injecting some high salinity water, and the oil recovery proceeds until we reach some plateau. And then what happens is that we switch to a low salinity injection brine, and lo and behold, some extra oil comes out of the plug. And that's very exciting because that oil would have huge value if we were able to replicate this process in a reservoir. So this is a so-called tertiary low salinity water flood. We've injected some high salinity water first and then switched to low salinity, and we see an incremental recovery of oil. We can also do something similar in a secondary process where we test the effect of injecting high salinity brine, and then we look at what happens if instead we start the experiment again and inject brine of lower salinity. So this is a secondary flood, and what we can see is that in this experiment, as we dilute the brine that we inject, we see incremental recovery of oil. So this looks great. What a simple, improved oil recovery mechanism. We just have to dilute the injection water and magically more oil is going to come out of the ground. However, so this was also extended to carbonate reservoirs, I should say, before we talk about the but. Those were both sandstones I showed before. People also showed this could work in carbonate reservoirs. So again, here we're showing the oil recovery in blue. And each time we dilute the injection brine, we see an incremental recovery until we get to these very high recoveries and very low salinity injection brines. So now's the right time for me to say, but everything looks good so far. We've shown it in sandstones, we've shown it in carbonates. So why don't we just go ahead and dilute the injection brine and see all of this extra oil produced? So people went away and did lots more experiments, and they also found things like this. So again, we're looking here at the data points in a circle. We've injected seawater. We switched to injecting a very dilute brine, and we see no response, no incremental recovery. And that was in tertiary mode, and we also see the same kind of thing happening in secondary mode. So here again, we've got two different oils. Each pair of curves represents a different oil with injecting different brines. And you see that here we see almost no benefit from injecting dilute brine. And there are published examples of failures and many more that you hear about if you chat to people doing the experiments. People don't like publishing failures, they like publishing successes. But there are plenty of examples of where dilution of the injection brine did not in fact yield improved recovery. So not as straightforward as we originally thought. So the sorts of things we don't know about controlled or at this stage low salinity water flooding, well, we don't know why it doesn't always work. Now, as we said, we see lots of core flooding experiments where we don't see a benefit from diluting. So if we don't really know why it works, we don't know how to identify candidate reservoirs without just doing lots and lots of core flooding experiments and hoping that we hit on some lucky brine injection composition that yields improved recovery. That's going to take time and cost a lot of money. We don't know how to predict the right brine to optimize recovery for a particular crude oil brine rock system. The one common thing that's been observed where low sal has been, or controlled salinity water flooding has been observed to yield incremental recovery, is that that seems to be associated with a shift from more oil wetting to more water wetting behavior in the core samples. And so that doesn't really help us very much. All it means is that instead of trying to understand low sal, maybe we should try and understand why we see this wettability alteration occurring and how this impacts on core to reservoir scale flow. So we're really talking here about a problem in wettability or wetting characterization and what controls the wetting behavior in natural rocks. So wetting, what is it? Well, it's the ability of a liquid to spread over a solid surface. The degree of wetting is called wettability, and it's determined by a force balance at the molecular level between the cohesive forces of the liquid and the adhesive forces that act between the surface and the liquid. So essentially, we're looking at molecular level processes that control wetting, which is why this is a multi-scale problem. If we look at the sort of length scales that we're trying to span here, our physical controls are down here at the molecular level, the nanometer level, but the impacts that we're interested in are at the kilometer scale in a reservoir. So we have some 12 orders of magnitude of length scale to span between trying to understand the fundamental physicochemical processes and what they're going to do in terms of reservoir production. So if we think about how we usually have traditionally characterized wetting behavior in the lab, it's been very much core-based. So again, we can do spontaneous imbibition tests or core flooding tests, and we can determine things like the AMOT wetting index or the USBM wetting index. But these are all rather crude. They're not very sensitive to changes in wetting. They're essentially qualitative, and they don't really tell us what's going on at the molecular level of interest. They don't tell us why wetting is a function of brine composition in different rock samples. So that's one of the reasons why there's been this huge explosion in research in controlled salinity water flooding over the past decade. People have been applying lots of new methods to try and understand wetting behavior across a range of different length scales. So I can add now essentially a whole range of different types and approaches of study which have been applied to understanding wetting behavior. And if I had a 2-hour lecture rather than a 30-minute lecture, I would be very happy to spend time going through all of these different methods and approaches. But I've just pulled out a few, and also a few kind of interesting papers you might look at if you had more interest in this area. So at the finest scale, we have atomic force microscopy that can actually probe the intermolecular forces acting at an interface using a very fine probe tip. We have very high resolution imaging using scanning electron microscopy and micro CT scanning, looking at the in situ distribution of fluids in a multi-phase displacement. We have more experiments on model systems, looking at adhesion of droplets onto model mineral surfaces, looking at the contact angle and the spreading of those droplets. There are dynamic experiments on micromodels, and then modeling attempts to try and bridge these very small length scales of characterization up to the scale of core floods, and then finally to the reservoir. And one thing I just wanted to highlight with these references is that this has moved now very much out of the traditional petroleum engineering research environment. There are lots of publications coming out in material science journals and so forth. And there are some reviews that you could have a look at. I published one a few years ago, and there's a more recent one looking particularly at time and length scales of low sal. But what I want to focus on is some work we've been doing, looking particularly at Zeta potential and how that is linked to wettability alteration and improved recovery during controlled salinity water flooding. Now, one of the things we know is that the key interfaces, the mineral brine and the oil brine interfaces in a reservoir rock during production are electrically charged. And there's several reasons why that is. on a mineral surface. You have imperfections in the lattice where which give rise to charged surface sites. In a crude oil, there are polar organic molecules, and at the interface, they can give rise to a surface charge. And these sorts of sites allow then pH-dependent reactions with dissociated water ions. So pH is often a very strong control on surface charge. And these sites also allow there to be adsorption of salt ions like calcium and magnesium, which are very strongly dependent on the concentration of those salt ions. And the Zeta potential is interesting because you can use it, you can measure it, and that can characterize the surface charge and the controls on surface charge like pH and composition. And from a wetting standpoint, the Zeta potential is important because it controls the electrostatic interactions at the mineral surface and between the mineral surfaces and other polar species you have present. So any polar species in the oil will interact electrostatically with the mineral surfaces, and any polar species in the brine, like salt ions, will interact electrostatically with the mineral surface. So we can see already that Zeta potential is potentially going to be important in controlling wettability, and that it will vary potentially during controlled salinity water flooding. So just to zoom in and sort of explain the Zeta potential a bit more at the mineral surface scale, we have a schematic here of a calcite mineral surface. And what we have here is a sort of a schematic representation of the distribution of different ions and molecules in the brine adjacent to that calcite surface. And what we have here is a sketch of the variation in electrical potential as you move away from the mineral surface. And it's important to say that these length scales are very small. So we're looking at length scales of order nanometers to a few tens of nanometers here. So we have some surface sites on the calcite surface owing to these imperfections. These surface sites can react with the dissociated water ions. We often call this the hydrolysis layer. And these sort of reactions are pH dependent, and in many materials like silica, in fact, these can dominate the Zeta potential. However, on calcite, what we see is that we have lots of adsorption of so-called potential determining ions, which here are calcium. They can also be magnesium, as we'll see, and carbonate ions. And in fact, it's this adsorption of these divalent ions that really controls the surface charge behavior of calcite, as we're going to see. And together we call these immobile ions, which are adsorbed onto the mineral surface, the stern layer. However, outboard of those, to balance the overall charge, we have also got some excess counter ions in what's called the diffuse layer. And this double layer or triple layer arrangement is neutral overall. We have some immobile charge here, and we have some mobile charge here. And we can sort of think about there being a shear plane, a nominal shear plane, outboard of which these ions can move relative to the mineral surface, and the electrical potential at that shear plane is defined as the Zeta potential. And this is the potential we can measure using a variety of different experimental methods in the lab. Okay, so material scientists know a lot about the Zeta potential. They've been measuring it for years, and in fact, you can buy some kit off the shelf to do this. Kit like zetameters or zetasizers or acousticizers, but they're not always ideal for our needs in terms of reservoir characterization. The first thing is you need to powder the sample. So you create a suspension of the powder in the electrolyte of interest, which for us means that we destroy the pore space, which we'd like to avoid if possible, because that is part of the natural makeup of the rock. They also have a pretty limited range of pressure and temperature ionic strength, particularly temperature and ionic strength. It's difficult to go to the high temperatures and the high ionic strength that we need to look at for reservoir applications. And you have one electrolyte, one fluid phase, whereas we know in reservoirs we have multiple fluids present. We have at least oil and water. So in nature, we've got intact rocks, we have high pressure, temperature, and ionic strength, and we need to account for the presence of oil and water. So that's meant that we've used a different approach to characterize the Zeta potential in our experiments in the lab. We do the experiments on intact core plugs, and we measure something called the stream potential. So a little schematic here of a pore, or a few pores. We have, in this case, a negatively charged mineral surface. We have the excess counter charge in that diffuse layer adjacent to the mineral surface. And if we cause the brine to flow through the pore space, some of that excess charge gets dragged along by the flow, that establishes something called the streaming current. That's balanced by a conduction current overall to maintain electrical neutrality. To drive that conduction current, we need an electrical potential difference. That's the streaming potential, and we can measure that during a flowing experiment in a core plug. And once we know this thing called the coupling coefficient, we can then calculate the Zeta potential if we know some other properties like the formation factor, the rock conductivity, the brine viscosity, and the permittivity. So we have essentially got a modified lab setup where we can do core flooding experiments and measure the Zeta potential at the same time. And we can do this at elevated temperature and high pressure, so we can replicate reservoir conditions. And we can also make measurements at very high ionic strength. The nice thing is that we can also do displacement experiments. So we can test how the Zeta potential changes as we measure incremental oil during a controlled salinity water flooding experiment. That's what we've been doing for the past few years. So what we did first of all was to start to explore the behavior of the Zeta potential at the mineral brine interface, at conditions relevant to reservoirs. So these are the sorts of experimental results that we get. What we're looking at here is time on the x-axis. On the left-hand y-axis, we see pressure, which is shown by the smooth line. And on the right-hand axis, we see the resulting streaming potential, which is shown by the somewhat jagged line. So we see that as we pump brine through the plug, we get an electrical potential difference, which I think is a really neat piece of physics. And the first thing I can tell is that the Zeta potential here is positive because the electrical potential difference responds in the same way as the pressure difference. Now this line looks a bit noisy, but look at the axis. We only have a few hundreds of microvolts here. And we're actually measuring the streaming potential at very high ionic strength, which would not be available if we tried to do this using a zetameter. So in fact, we can measure very small electrical potential differences here, and from that we can determine the Zeta potential. So we do these sorts of experiments at several different flow rates. We do a cross plot of the measured streaming potential against the measured pressure difference. We put a regression through that, which gives us that coupling coefficient, and from that we can work out the Zeta potential. So now it's time to do lots of experiments. And I'm not going to go through all of the results that we've produced, maybe just some of the most important ones. So again, going back to carbonates, I said that calcium was very important in determining the Zeta potential. We see the evidence for that here. What we're doing is plotting the Zeta potential as a function of the concentration of some of these key ions, calcium and magnesium, and also sulfate. And we're plotting it as PPDI, as an analogy to pH. Okay, so H, the proton isn't important here, it's the calcium or magnesium concentration. So we're treating these as being the potential determining ions. And what you can see is that if we have dilute calcium or magnesium, we have negative Zeta potentials, but as we add calcium or magnesium, the Zeta potential becomes less negative, and eventually we can even invert the Zeta potential and see positive values if we add enough calcium and magnesium. And in fact, calcium and magnesium are acting almost identically here with an experimental error, whereas sulfate has the opposite effect and seems to be much less significant. If we add a load of sodium, so we make this much more saline, but we add something which is quite indifferent, like a sodium ion, then as we add more and more sodium, so the sensitivity to calcium goes down. And we can also look at what happens if we test out different carbonates. And so what we have here is 3 different types of carbonate, and in fact 2 of them behave very similarly, and another one behaves rather differently. And we think this may be related to the orientation of the mineral surfaces and edges in the pore space. But the message is that different carbonates exhibit different behavior. So this has all been done using sort of very simple electrolytes, but what we're really interested in oil reservoirs are complex electrolytes, high salinity formation brines that contain a real mix of ionic species. And also everything I showed you there was at room temperature, whereas what we're really interested in is elevated temperature. And we want to be able to switch between typical high salinity and low salinity brines. So that's what we've been doing more recently. What we're looking at here is a plot of Zeta potential for different samples. Okay, so each of these different bars represents a different carbonate sample, and the red lines are for typical formation brines, and the blue lines are for typical dilute brines. And there are some different temperatures here, and there's a lot we could sort of go through in this figure. But perhaps the most important thing for this talk is the fact that as we go from a high salinity formation brine to a low salinity dilute brine, we see pretty consistent behavior, which is that we switch from having a positive to a negative Zeta potential. So by and large, in carbonates, we've seen this pretty consistently across all the samples we've measured. As we dilute from high to low salinity, we expect to see more negative Zeta potentials on the mineral surfaces. So we need to bear that in mind when we look at what happens next when we add oil. So that's the next thing. We need to be able to account for the presence of crude oil that can preferentially wet the mineral surfaces. Now, we looked at this quite a few years ago, and we came up with a very simple conceptual model. You know, if we have a water-wet, water-occupied pore, which is shown by this triangle here, then of course the Zeta potential we measure will just reflect the brine mineral interface. But if we have wetted those mineral surfaces with crude oil, then in fact that's going to hide the mineral surface, and the Zeta potential we're going to measure in an oil wet sample will in fact return the Zeta potential of the oil brine interface. So if we do flooding experiments on oil wet samples, we expect to get some insight into the Zeta potential of the oil brine interface, not the mineral brine interface. And what you see here is that this is a carbonate, so we think we have positive Zeta potentials on the mineral brine interface. But at that time, we thought that the oil was pretty much always negatively charged, and so we would expect the oil wet mineral surfaces to return a negative Zeta potential. So what we then did was to age a bunch of samples in different crude oils and test how the Zeta potential changed before and after aging. So what we look at here is the y-axis here shows the change in Zeta potential after aging. So the Zeta potentials we initially recorded would be in the water wet conditions would be over here. And if they become more positive after aging, we plot in this direction. And if they become more negative after aging, we plot in this direction. And the x-axis shows us a measure of wetting. It's the AMOC water wetting index. And so over here at the right-hand end, we're pretty oil wet. And that shows us that we did a good job of aging the samples in the crudes of interest. And what we see here essentially are two different trends. Okay, so that's our water wet sample, which is initially positively charged. And then after aging, we see a trend where the mineral surfaces, or the samples, sorry, return a more negative Zeta potential. They're oil wet, and we interpret that as reflecting, as I said, the negative Zeta potential on the oil wet mineral surfaces. That's the oil brine Zeta potential that we're seeing here. That's what we expected to see. What we didn't expect to see was this trend here. Because if the Zeta potential gets more positive after aging, there's only one way we can interpret that, which is that in fact for these crude oils, the oil brine Zeta potential is positive, and in fact even more positive than the carbonate mineral surface. And that was a real surprise to us, and we did lots of measurements to confirm that what we were seeing was real. So of the 7 crude oils that we've tested so far, 4 of them were negative, but 3 of them were positive. So it's not like it was a one-off either. You know, it's almost 50-50 now between negative and positive crude oils. And we expected to see negative crude oils. So what are the consequences of this for low sal? Well, we did a conventional dilution experiment with one of those negative oils. And what we saw was that we got an incremental recovery as we went from formation brine down to dilute brine. But when we did the same experiment with one of the positive oils, we saw no response to low sal. So then, and you'll kind of understand the perhaps the hypothesis for this, what we tried doing next was the opposite. So what we did was we took one of those positive oils and thought, well, what happens if we increase the salinity rather than decreasing? We start off with a dilute brine and end up with a formation brine. And in fact, what we saw was incremental recovery, which is why I don't call it low sal anymore. You can get incremental recovery by either increasing or decreasing the salinity so long as you do it in the right way. It's the change in Zeta potential which is key, not the salinity. So we can develop a very simple kind of mineral scale model to explain these results. We can use a DLVO type model, De Janguin, Landau, Verwey, and Overbeek, who are interested in the forces that act between 2 interfaces in aqueous solution. And we can think of the oil as being one interface and the mineral as being the other interface. And they looked at a whole range. They looked at electrostatic, van der Waals, and structural forces. We're focusing here on the electrostatic forces because we know they change a lot as we change the brine composition. We saw that through that big change in Zeta potential. The model is pretty simple. If we have a negative oil and we have an initially positive mineral surface, there's going to be an attraction. If when we dilute the brine, we make the mineral surface more negative, there's going to be a repulsion. It's going to push the oil off the surface, and we're going to re-establish a stable water wetting film. So we're going to move back to more water wet conditions, which is consistent with the observation during low salinity water flooding. However, if we have an oil-water interface with a positive Zeta potential, making the mineral surfaces more negative is not going to help. In fact, you're going to increase the electrostatic attraction between the oil-brine interface and the mineral-brine interface. To get improved recovery here, you need to make the mineral surfaces more positive, and that's what we do when we switch from a dilute brine to a highly saline formation brine. We make the mineral surface more positive, and now we get that electrostatic repulsion, and now we see the switch to more water wetting conditions, and then we see incremental recovery. And our hypothesis is that when studies have failed to observe improved recovery using the conventional dilution low cell approach, the reason is that they were dealing with a positively charged oil and didn't realize. And so you were never going to get a response by diluting in that case. And if we look across all of the experiments that we've done, we can see a correlation between incremental oil recovery, a reasonable correlation, okay, and a normalized change in Zeta potential that accounts for the change when we dilute the brine or change the brine composition, and the change that we see after wettability alteration. So that all sounds very simple. I'm nearly done, but there's a bit of a sting in the tail, okay? I looked a lot here. I talked a lot about the mineral brine interface. And I talked about how changing the Zeta potential, the mineral brine interface, could affect the electrostatic forces. And I kind of didn't talk very much about the oil brine interface. And in fact, we initially assumed that was going to stay constant, but it doesn't, okay? If we look now at the Zeta potential after aging for a given crude oil in formation brine and in low salinity brine, we see evidence that the oil brine Zeta potential can change as well, okay? In here, the Zeta potential after aging became more positive, and so we interpret that as being a positive Zeta potential at the oil-brine interface. But here we saw the opposite in low salinity brine. The Zeta potential became more negative after aging, and we have to interpret that as being a more negative Zeta potential on the oil-brine interface. And in fact, this one is a bit ambiguous. It's either positive or probably less negative. So in fact, the oil brine Zeta potential is also going to be a function of the brine composition. And there's several reasons why that might be, although we're extremely short of data at the relevant conditions of temperature and salinity. What we know is that we have polar species, we have acid and base groups in crude oils, and they themselves can undergo pH-dependent reactions. So we have a pH dependence of the crude oil brine Zeta potential, and it's been observed if you go to very low pH, you can get positive Zeta potentials in crude oil, but only with dilute brine so far. So maybe it's all about pH and kind of the acid and base number of the oil, although we've seen no correlation with that in our experiments. And the other possibility is that, again, we have some concentration-dependent cation adsorption, particularly onto the acid groups. So maybe this, again, is all around changing the calcium or magnesium concentration in the brine, and that also affecting the polarity of the crude oil brine interface. So where we are with this is, first of all, it's not low salinity water flooding, it's controlled salinity water flooding. You don't need to inject a low salinity brine to see incremental recovery. If you want to design the right brine composition, then you need to know the polarity of the minerals in the oil, and then you want to change the brine composition in a way that maximizes the electrostatic repulsion between the crude oil brine interface and the mineral brine interface. But the sting in the tail is that the oil brine Zeta potential can also vary with brine composition, and at the moment we just don't have enough data to confirm the kind of modeling that's been done to predict how this would happen at reservoir conditions. Okay, so that's me done. If I'm allowed to have 2 more minutes from Hadi, I have 2 little encores.
Yeah, please, yes.
So the first encore is that I talked a lot about carbonates. What about sandstones? So I just want to show 2 indicative sets of results from some sandstones. So this is a conventional negative low sal flood with one of those negative oils, and we see incremental recovery. So that seems to hang together. And we've also done the inverse low sal with one of those positive oils in a sandstone and also seen a recovery. So far, the model that we developed originally from carbonates still seems to make sense in sandstones, because in sandstones, you still expect to see more negative Zeta potentials as you dilute from formation to dilute brines. And the second thing is that I haven't really said, I've talked about mineral scale Zeta potentials, I've talked about core scale kind of recoveries. How can we go about trying to better bridge those length scales? And I just want to flag up some work that that Sebastian did with one of my ex-PhD students and one of Sebastian's current postdocs, Julian Mays. And what this modeling is doing is basically saying, well, okay, let's look at flow in the pore space. Let's look at how salt ions will be transported with the flow. Let's use a model that relates the salt concentration to the mineral surface potential. So that could be based on experimental data that I've derived, or it could be based on a surface complexation model. And then let's link that Zeta potential change to a change in wetting behavior. And again, that's something we could get out of experimental data and see what happens. Because one of the mysteries of this switch from more oil wet to more water wet conditions is that lots of core flooding experiments done in the 90s said that in fact you saw the highest recovery for intermediate or mixed wet systems. So it's not really always clear why shifting to more water wet conditions should be good for recovery. And the trick really is around how this interacts with a displacement dynamically, where the contact angle is changing in response to the composition of the injected brine. And what we see here in this, simple kind of 4-pore model is that we leave more oil trapped when we just inject formation brine than if we inject a dilute brine. So we start to see a link here between the mineral surface scale mechanisms that control contact angle and wetting behavior, and how that would influence a displacement at a larger pore scale, which could also then be scaled up to the core scale and then the reservoir scale. Anyway, that's all for me. Thank you very much. And I guess, do you have any questions?
Yeah, thank you very much, Matt. I'm not sure if you could clap, but I'll try to do that for you. Thanks a lot. Now the chair is Sebastian, will chair the discussion session.
Hi, Matt. Thank you for the nice talk. The questions are coming in quick and fast. I'm just trying to scroll back to the very first one. There was a comment from David Wilkinson, who said the performance of the recent BP Clearage field will be interesting, hopefully beneficial. I guess that's more of a comment. Alexandros Danilidis asks, is there a way to anticipate the oil behavior based on its composition?
Not that we know of yet. So the real issue is going to high ionic strength and high temperature. So there have been some surface complexation models that have been developed, and they've been validated against a very limited data set for the Oil-brine Zeta potential. It's really hard to measure the Oil-brine Zeta potential. You have to make if you use a zetameter, you have to make an emulsion of the oil droplets in the electrolyte, the brine of interest. That emulsion has to remain stable enough for you to make a measurement. And as you increase the brine salinity, what's keeping that emulsion stable is the electrostatic repulsion forces between the oil droplets. As we make the brine more saline, those electrostatic repulsion forces go down, and so it's harder and harder to maintain a stable emulsion of oil in brine. So it gets really difficult to measure the Oil-brine Zeta potential at anything approaching sort of even seawater, let alone going to sort of formation brine. So it's, and then trying to do that at high temperature is even more difficult. So I think that I think that there will be some models, but we need to have a better experimental data set against which we can validate them. With surface complexation models, there are so many different dials you can turn on the inputs. You can tweak all kinds of partition coefficients and surface site densities and so forth. You really have to have a good experimental data set against which you can constrain the model predictions. Otherwise, they can almost tell you anything you want. So that in my view. So I think what we need to find is some ways to be able to measure the Oil-brine Zeta potential at the conditions of interest. And we are looking at that. So one of the things we're thinking about is whether we can extend the streaming potential method to very strongly oil wet porous media. So if you imagine using something very hydrophobic and you coat it with the crude oil, and you hope that that crude oil remains stable during a streaming potential experiment, we can then use the same method that we've used for the mineral brine interface to probe the oil brine interface and go to these high ionic strength conditions and these high temperature conditions.
Okay, thank you, Matt. Next question is from Pat Corbett. Would like to know how the controlled salinity flooding effect varies with rock type characteristics, things like tortuosity, shape factor, surface area.
So the main effect we've seen there is in the initial wetting behavior. So okay, there's two things that we've seen where rock texture seems to be important. So one of them is in the initial wetting behavior. So we've seen, for example, I mean, and I didn't really get a chance to go on to this. You know, this I showed in my schematic of the DLVO model, these sorts of asperities on the mineral surface, but I don't really talk about them very much. I think they're really important, and I think some of the work that came out of Shell looking at the SEM imaging showed this as well. These are very important in being locations, these asperities where you're more likely to break down the stability of the wetting water layer, and also as pinning points when you have moving contacts. And so I think rock textures, we found it to be very important in the initial wetting behavior, and we've also seen it potentially, because I mean some samples we just can't age them if they are very rounded smooth grains. They just seem to be very difficult to break that wetting water layer, even if the electrostatic forces should be favorably acting. So you seem to need these asperities to give you these weak points in the wetting films to actually start to get this process working and then allow the contacts to recede away from those. And we've also seen some textural controls on the Zeta potential. So this is quite kind of difficult to, we see some evidence looking at thin sections and micro CT images that whether you have faces or edges more exposed to the brine in the pore space, they can have quite different Zeta potential characteristics because of the lattice structure effect. And that, because the Zeta potential is the thing that we're sort of seeing as the controlling variable, those texturally controlled variations in Zeta potential can also then affect what we see in the loci behavior. Beyond that, no, but then we probably haven't yet explored a very wide range of different sort of rock types with varying tortuosities and so forth.
Thank you. Hosseini Nasser would like to know if there's any field or pilot application for low salinity flooding in carbonate reservoirs. If it has been done, is there any success?
That's a very good question. I'm not up to date with the literature on pilot tests. I mean, certainly Aramco have been very keen in pursuing low-sal, and they've put out a lot of papers in literature about laboratory experiments on low-sal, and also have, you know, sort of not just core flooding, but have expanded to look at some of these other methods for trying to characterize the intermolecular forces, the wetting behavior, and so forth. I don't personally know whether that has propagated yet into a field trial, and if anyone else on the call has any information about that, then, you know, please do let us know.
Thank you. Maxim Yutkin, thanks you for a very interesting talk. I would like to know, there have been 10 years of research into experimental streaming potential measurements. Have you settled on understanding why there is a measured potential from the diffuse layer where the DLVO theory predicts 0?
Yeah. Okay. So again, not something that I was able to get into in this talk, but a question from somebody who knows, you know, a lot about this. So that was actually one of the reasons why we started doing the experiments in the first place. So the Zeta potential it typically decreases with increasing ionic strength if you're just looking at the mineral brine interface. And the reason is that diffuse layer I talked about becomes thinner and thinner as the brine ionic strength increases. And essentially what you have is you have more and more ions packed into that diffuse layer, and so it more effectively shields the charge on the mineral surface. And so if you extrapolate experiments made at low salinity into the high salinity domain, you predict that the diffuse layer collapses completely, and you would have no Zeta potential because there would be no mobile charge